Vi, whichever we have. So which will be in the form of Vi is equals to, so the input voltage, the sinusoidal input voltage, whichever we are going to be apply here, Vi, which will be equals to E naught sine omega t, we are going to be apply. So the input voltage, sinusoidal voltage, which we are applying is Vi is equals to E naught sine omega t we have. And the frequency of this sinusoidal voltage will be equals to F is equals to omega by 2 pi we have. The frequency whichever we have is F is equals to omega by 2 pi is the frequency which we are going to be applied to the circuit, which is consisting of a resistance and a capacitor in series. So generally, if you see the circuit will be like this, we have a capacitor and a resistance here. So these are connected in series. Here we are applying input voltage Vi here. 1 minute. Vi we have. So this we have like a input voltage will be applied to this RC circuit. So this is a capacitor and this is the resistance which we have in series. So input voltage which we are applying is Vi is equals to E naught sine omega t, and the frequency is F is equals to omega by 2 pi, which is applied to the circuit which is consisting of this resistance and capacitor in series. Okay. So this alternating current in the circuit leads the applied voltage Vi, the alternating current here, AC, whichever we are going to be called. So this leads the applied voltage Vi by an angle phi, it is going to be lead here. So this, which is given by tan phi, which will be equals to 1 by omega CR, which we have. So generally omega is nothing but 2 pi f. So therefore it will be omega is 2 pi f CR you are going to be having. So this value of phi, whichever we are having here, this depends upon the values of resistance and capacitance, which we will connected in series in the circuit. So the values of R and C may be chosen so that for frequency F uh, and phi is equals to 60 degrees. So if you build a ladder network here, which is consisting of the resistance and the capacitance in different sections. So like this, if you have a combination of uh, capacitor and resistance, so here, so again another capacitor is connected. So here we have, so one more capacitor to connect here in series. So here we will apply this input voltage, which is consistent of V I is equals to E naught sin omega t, and here we can take the output here. So here one RC combination will be there. So this one R and C. So we will be choosing the values of R and C, maybe chosen such that the frequency F comma phi is equals to should be phase difference should be 60 degrees. So here if you build a ladder network which is consisting of three RC combinations. So uh, here we have this one as we see here. Uh, this one RC combination. So this RC combination, you are going to be get a phase difference of 60 degrees because as we have to choose the frequency, we have to choose the resistance capacitance value in such a manner that phi should be 60 degrees, that is phase shift should be 60 degrees. So this combination, you are going to get 60 degrees of phase shift. Another RC combination, again, you are going to get another 60 degrees of phase shift. So this RC combination, again, you are going to get 60 degrees of phase shift. So consequently, as we have been using three RC combinations we are using here. So as we are using three RC combinations we are using. So each RC combination you are going to get a phase shift of phi of 60 degrees you are going to get. So therefore 3 into 60 degrees you are going to get 180 degrees of phase shift you are going to be produced between the this input and here this output. Okay, so in between this input and output, you are going to get a phase shift of 180 degrees. You are going to be produced here. So here we can say that the output voltage, if you take it as a VO, is the output voltage if you take. So this VO output voltage leads the voltage input, V input, by how much? 180 degrees of phase shift. So V output leads the input voltage VI by 180 degrees. It is going to be produced. So this is the principle which is involved in the case of the RC phase shift oscillator. So now we'll see the circuit diagram and as well as the operation of this RC phase shift oscillator. So first we'll draw the circuit diagram of this one. So here we'll take the what we call the circuit diagram as well as the operation. So first we'll take this circuit diagram of RC phase shift oscillator. So now here in the circuit as we have one NPN transistor which consisting of three terminals as a base collector as well as this emitter here. So there is a resistance connected to this collector as well as this one more resistance there. This is another resistor. This is emitter. Emitter connected with the resistance and then capacitor here. Similarly here will be connected to plus VCC plus VCC. So now this combination is connected to ground here. This is a collector from this one capacitor. This is the RC combination which we have, and another capacitor. So here we have a resistance, another capacitor here. Here we will connected another resistance. This resistance will be given as a feedback here. Yeah. But this resistance, we write it as a R1. This is a resistance 2. This is the load resistance. It is the emitter resistance. It is emitter capacitor. So these values, we have the same values of our C. So this is R, this is R, and this is resistance is this resistance we take it as Rx. Then I'll explain later. We have to get that as a R value. So as we have see the circuit diagram. So in this a NPN transistor we have taken. So this NPN transistor in common emitter configuration we have been connected. Emitter is common for input as well as the output. So it is a common emitter configuration we have been connected. Here we have a load resistance RL in the collector circuit and the resistors R1, R2, as well as we have RE, R1 resistor, R2 resistor, and RE resistor. This provides the necessary biasing condition for the circuit here. And here CE is nothing but this is an emitter bypass capacitor we have. So for feedback of energy from the oscillator, uh, from this what we call a feedback of energy from this collector to base here, collector to base here. A ladder network here we have that is a RC combination. This is RC, this is another RC, this is another RC. So this consisting of three identical RC combinations we have. These RC sections is connected between the collector and base here. So between the collector and base, it has been connected here. So the last section, if you take here RC, here we have been taken a resistance as Rx we have been taken. So this resistance Rx actually it should be equals to R, but how the value R will be equals to Rx will become Rs. R is equals to combination of Rx plus HIE we have. HIE we have. So here HIE is nothing but this HIE is nothing but the input resistance of the transistor. So this is the input resistance of the transistor. So since this is resistance is connected with the base of the transistor, the input resistance HIE of the transistor is added to give a total resistance of R. So this Rx plus HIE will total becomes R here. So actually here it should be this should be R. So this R will be equals to the combination of Rx plus HIE. So this Rx is the resistance whichever we have been taken, and HIE is the what call input resistance we are going to be had here. So this is going to be added up to give the total resistance as R we are going to be get here. Now the circuit is set into oscillations by any random variation caused by the base current by the minor variation in the oscillations of power supply VCC. So variations in the oscillator power supply VCC here. So are by the noise inherent in the transistor we are going to get here. So this variation in the base current is amplified in the collector circuit and then feedback into the RC network here. So this amplifier, what it is going to be do is it will be amplifies the signal and it is going to be given here output. So the collector circuit has then feedback here. So this collector circuit here, this total, it is going to be RC network. It is going to be feedback to the base here. So the network produces phase shift of 180 degrees produced by the common emitter. Already we have seen. So this RC network, whichever we have. So this RC network here, this RC network is going to produces a phase shift of 180 degrees. It produces 180 degrees of phase shift it is going to be produced. Okay, phase shift it is going to be increase 180 degrees of phase shift. So additional phase shift of 180 degrees we require so that additional phase shift of 180 degrees is produced by the common emitter transistor. So here, with the help of this common emitter transistor, this is going to be produces CE transistor. The CE transistor, it is going to produce 180 degrees of phase shift. So 180 degrees of phase shift it is going to be produced. So the total phase shift around this entire loop, it is going to be 180 plus 180, 360 degrees of phase shift it is going to be produced here. Total 180 plus 180, total 360 degrees of phase shift, or we can say that 0 degrees of phase shift it is going to be produced here total. Okay. So now we'll move to the analysis of the circuit here. So analysis of circuit here, what we'll do is we will draw the equivalent circuit of this one. So here equivalent circuit will be in this manner. So here equivalent circuit we are drawing here. Equivalent circuit. Second RC combination, as well as this is the third RC combination. So this third RC combination is going to be fed back. So here in this manner we have. So here it is a HIE. So these capacitors as C we have. So this is one resistance R. This is the second resistance. And this third resistance, which is going to be have a value as 1 by HOP here. So this uh, Rx, whichever we have, this will be equals to R minus HI. We are going to be have this total is going to be fed back here. So this is what the equivalent circuit which we have here. So here in this circuit, this 1 by HOE, whichever we have, okay. So this uh, 1 by HOE to this part. So 1 by HOE can be neglected because it is much larger than RL value. So it can be neglected because it is larger than RL value. So now we have like a, here we have HIE V2 here. So this value, which is equals to HIE V2 here. So this HIE V2 can be neglected because of HRE of a transistor, which is very small here. Therefore, the equivalent circuit of phase shift oscillator, whichever we have here, this can be replaced, otherwise it can be reduced to another equivalent circuit, so which we are going to draw here. The equivalent circuit of the previous circuit which we have, we can draw here. This is what the equivalent circuit which we have here. So this is load resistance RL we have. So generally the capacitor values all are the same. C is going to be have. The resistance value of this is R. So there is a connection between this and this is also R. And the third one is also R we are going to have. So the current which is flowing in this first is I1. Current which is flowing in the second is I2. And the current which is in this section is I3 we have. So as we have taken this one, so the equivalent value of this uh, circuit will be here HFE I2RL we are going to be happy here. So this is HFE I2RL we are having. So now the previous equivalent circuit whichever we have, so this can be replaced by this equivalent circuit. So this is replaced by this equivalent circuit whichever we have drawn here. So here the current source HFE-I3 has been replaced by an equivalent Thevenin voltage source generating as HFE-I3 RL here. HFE-I3 RL here. Okay. So the previous source, current source HFE-I3 here in this one, HFE-I3 in this one. So it has been replaced by this circuit. So here we have HFE-I3 RL. This one. So now we have to apply the Kirchhoff's uh, voltage law. We have to apply in these three meshes. So the first mesh, the second mesh, and third mesh. So in these three meshes, we have to apply the Kirchhoff's voltage law. So by applying the Kirchhoff's voltage law, we can get it as a equation as RL plus R minus JKXC here this one into I1. This is in the first mesh we have been applied. In the second mesh, in the RI2 we have the in the third mesh we have like a HFE I3 RL, the third mesh. So this total value is equals to 0. This total value is equals to 0. So we have applied the Kirchhoff's law to all these three meshes so that we have got RL plus R minus JXC minus JXC into I1 minus RI2 plus HFE RL I3 which we have been applied. So this we can solve so that we can get it as a minus RI1 plus 2R minus JXC into I2 plus sorry, minus RI3. So which is equals to 0. So we have solved this one. We current value we have written. So here this value R value is equal to 0. So therefore, it will be, so if you solve this further, so you are going to get 0 into I1 minus RI2 plus 2R minus JXC into I3, which is equal to 0, you are going to get. Okay. So for the three meshes, we have applied this what we call Kirchhoff's voltage law here. So we have got these three equations we have been got. So now what we'll do is here we have written XC, which XC is nothing but which is equals to 1 by omega C. So this XC is nothing but it is a capacitive reactance. Capacitive reactance. This we have. So now for since the currents I1, I2, and I3 are non-zero, the determinants of the coefficients of I1, I2, and I3 in the equation 1 through equation 3 must be 0. Okay, so the determinant must be 0 in the equation 1 and equation 3. So therefore, we can write that here. So here we can write that. So we have like the determinant value as, here we have the determinant as first one we have RL minus plus R minus JXC, this one. And next in the next term we have is minus R, and the third term we have HFERL. So HFERL. So once applying this Kirchhoff voltage law to the three meshes, we are writing here to find the determinant minus R. Next we have a 2R minus JXC. Next third one we have minus R, and here in this case it is 0. Next one is a minus R, and the third one is the determinant is a 2R minus J, this is a XC. So this determinant should be equals to 0. So this we have to find out here. So now we will write the values of this determinant equation. Right. So if you apply this, we are going to get it as first one is RL plus R minus JXC into this minus this one you are going to get. So that we are going to get it as a RL plus R minus JXC into we are going to get it as a 3R square minus 4R JXC plus XC square we are going to get minus R square into 2R minus JXC plus third one HFE into RL into R square, which is equals to 0. So here, by using this determinant of the matrix, we have got this equation. First one, we have to take this RL into this minus this one. Next one, minus R into this into this minus this. And third one, HFE into RL into this minus this. We are going to get this is the final equation which we are going to get. So this you take it as equation 5. Okay. So now we equating the imaginary parts of this equation 5 to 0. Otherwise, equating the imaginary part in equation 5. Otherwise, imaginary part of equation 5. Yeah. So that if we equate the imaginary parts, first we'll get it as a minus 4R XC plus RL plus R. This is one. Minus XC into 3R square minus XC square plus R square XC, which will be equals to 0. This we have been equated, imaginary parts. Now further solving this, we can get it as a minus 4R RL. Next it will be minus 4R square minus 3R square plus XC square plus XC square plus R square is equals to 0. Therefore, if you solve this one, we get it as a XC square is equals to 4R plus 4RRL plus 6R square we are going to get. So this is equation 6. The next, here we have got XC square is equals to 4RRL plus 6R square we have got. So from this, we can get the value of this XC square as we can write it as a 1 by omega square c square, we can write omega square c square x square, which is equals to 4r rl plus 6r square we have. So therefore, if you want to get the omega square value, so it will be equals to 1 by c square into 4r rl plus 6r square. This one. So therefore, if you get the value of omega, if you write it as a 2 pi f, so if you want to write the f value as a frequency of oscillations as f is equals to omega by 2 pi, so which we can write it as a 1 by 2 pi c root of 4 r rl plus 6 r whole square. So this one is equation number 7 which we have. So in general, this load resistance is taken, which will be equals to R. Then the frequency of oscillations, which we getting it as a F is equals to 1 by 2 pi R C. This total value is equal to 10 because what we are taking is the value of RL, that load resistance. Generally, we are going to take it as a R. We are going to take. So when we take this load resistance is equals to R, then we getting the frequency of oscillations is equals to 1 by 2 pi RC root 10 we are going to get here. So this is the frequency of oscillations we are going to get here. Now, similarly, we will get the condition of sustained oscillations for the phase shift oscillator. So in order to get the condition for sustained oscillations, what we have to do is we have to equate the real parts of this equation previously, which we have written here. So in this equation number 5, here we have to equate the real parts here so that we get the condition for the sustained oscillations we are going to get. So now what we do is now equating the real parts. Now equating the real parts of previous equation, which we have written as equation number 5. So in this equation, if you equate the real parts, we will get it as a RL plus R and into 3R square minus X square minus 4R square, 4RX square plus HFE RL R square, which is equals to 0. Here we are going to get. So if you write the real part, so first we are getting it as a R, RL plus R into 3R square minus XC square minus 4R XC square plus HFE RL R square is equals to 0 we are going to get here. So if you solve this further, so by using this previous equations and all, so we get the value of HFE, we are going to get it as a HFE, which we are going to get it as a 23 plus 29 R by RL plus 4 RL by R we are going to get here. So this is the equation which we are going to get here. HFE one. So here again, as we have taken in the previous one, the load resistance as we have taken it as a R we have taken. So again, here also we will consider the load resistance RL is equals to R. Then this equation HFE, it is going to be become it as a 56 here because it is a 23. So 23 plus 29 plus 4 you are going to be have because RL and R value is same. So these values get cancelled here. So this value get cancelled. So it will be 23 plus 29 plus 4. So that is nothing but 33 plus 33. We are going to get it as a 56. So HFE value we are going to get it as a 56. So for sustained oscillations in phase shift oscillator, the minimum value of the forward current gain ratio of the transistor should be 56. Okay. The current gain ratio of the transistor should be 56 we should have. So this is what we have about phase shift oscillator. So we have taken studied about the phase shift oscillator. So this is a principle. What is the principle which is involved in this phase shift oscillator is the applied voltage here in the input is Vi is equal to E naught sin omega t we have. So which is AC which we are going to be applied here. So the resistance RC combination we have to choose in such a manner that it is going to be produce a phase shift of 60 degrees. So now if you take like in such a combination as a three RC combinations, if we take so these three RC combinations, we are going to produce 180 degrees of phase shift. Then after there is a phase shift of 180 degrees in between the input and output you are going to be have. So that is a output voltage here. It is going to be leads the input voltage by 180 degrees here. So as we have seen, the output voltage is going to be led by 180 degrees input. So this is what we have seen. This is the principle here. Then after we have the circuit diagram here. So here we have drawn the circuit diagram. So in this, we have taken the three RC combinations here. So we have R1, R2 resistors. So RL is a load resistor which we have taken, which is connected to the collector. R1 and R2 are the two resistors which are going to be bias resistors we have. So R1, RE is a emitter resistor and C is the emitter capacitor, which we call it as a what we call bypass uh, capacitor we are going to be called. Then after this, we have like a this part, whichever we have. So this is a RC combinations with the which is going to be given into the feedback here. So this resistance Rx we have taken because already we have a uh, resistance, input resistance as RIE due to this total we have. So therefore Rx plus RI, Rx should becomes as a R. That is the condition which we have to take here. So therefore here this is the circuit diagram of a phase shift oscillator. Then after the equivalent circuit of this circuit diagram we have drawn. So this is the equivalent circuit. So in this again we will be neglecting some resistors as well as this. We'll get this is the final equivalent circuit which we have got. So this is the final equivalent circuit which we have got. So for this equivalent circuits, as we have three meshes here, first one, second one, third one. So now we will applying this what we call Kirchhoff's voltage law, KVL. We are applying to these three meshes so that we have got these three equations we have got first, second, third. And here XC, whichever we have written, it is a capacitive reactance, which will be equals to 1 by omega C. Then we will take the determinant of these three equations we have taken. So this is what we have written. So then after solving this, we have got x square, that is nothing but x square is equal to 4r RL plus r 6r square we have got. Then we have written x square as 1 by omega square c square we have been written. So which we have got this one. So omega square is equal to, we can get it as this is the omega square value we have got. So now for omega is nothing but the 2 pi f. So therefore frequency of oscillations f is equal to omega by 2 pi we can write. So that we have got this equation 7 here. This equation 7 as 1 by 2 pi c root of 4 r r l plus r 6 r square we have got. So generally what we'll do is we will take this load resistance is equals to resistance, general resistance value we are going to take. So RL is taken equal to R. So then the frequency of oscillations of the phase shift oscillator, we are getting it as F is equals to 1 by 2 pi RC root 10 we are going to get. So similarly, we can find out the condition for sustained oscillations. So in order to find out the condition for sustained oscillations in this equation previously, whichever we have got. So in this equation, so what we have to do is we have to make the real part equal to 0. So we have written the real part and we have made it equal to 0. So by solving this, we are getting this HFE value as this one, 23 plus 29 R by RL plus 4 RL by RL we are getting. So general again, we are going to take this load resistance value is equals to R. We are going to be put, then we are getting HFE is equals to 56. We are going to get HFE value is going to get as a 56. That is nothing but the condition of sustained oscillations. Otherwise, in order to get the sustained oscillations in this RC phase shift oscillator, if you want to get the sustained oscillations, then the minimum value uh, of forward current gain ratio, the minimum value of the forward current gain ratio should be equals to 56. If it is having 56 and more, then only you are going to get this sustained oscillations you are going to get. There is condition for sustained oscillations you are going to get. So this is about a phase shift oscillator. Then we'll move to another one, that is a Wien bridge oscillator. Then we'll move to next one, that is a it's called a Wien bridge oscillator. Wien bridge oscillator. Right. So in the case of the Wien bridge oscillator, so this is also a RC oscillator only, which finds wide use in variable, like in order to produce this audio frequency. So this Wien bridge oscillator is used. So this, in order to produce the audio frequency, as we have seen that in the case of the classification of the oscillators, different type of oscillators we are going to see. So this Wien bridge oscillator, which is going to be produce audio frequency range, it is going to be produced. So Wien bridge oscillator is nothing but the product, it produces the audio frequency oscillations it is going to produce. So it is a low frequency, low distortion sine wave generator. So it has the advantages over the phase shift oscillator, that its frequency may be varied over a range of 1:10 by varying one single capacitor. So if we change the capacitor, then we can vary in between the 1:10 ratio. So now we'll see the bridge network principle in this case. So as you said that it is a RC combination only. So this is a RC, both are connected in series here. And as well as we will be connecting this in a parallel also. So here, this is the circuit diagram of a typical bridge network principle. So here we will be applying input. So here we have the output here, right? So this is a R1 C1 and this is a R2 C2. So this is a Wien bridge network which is shown here. So the upper arm of the here, the upper arm here, which consisting of one resistor and capacitance in series, while the lower arm here, R and C, that is R2 C2, it is a combination of a parallel we are going to be have. Okay. So the ratio of the output voltage of the network to the input voltage of the network, generally we'll call it as a gain. So here V output by V input here. So this is the impedance of the parallel combination. So the total impedance generally we are going to be have. So this V output by V input we can calculate here. So this V output by V input we are going to get here as a certain value like minus JR by omega C by R square minus 1 by omega square C square minus 3JR by omega C are going to get here. The phase shift will be zero if the imaginary part of the term will be 0, that means it is going to be vanishes. So generally we'll have this one imaginary part will be equal to 0. So it will be on this value r square minus 1 by omega square c square is equal to 0. So from this we can get the omega value as 1 by rc we are going to get. So therefore frequency of oscillation f is equals to omega by 2 pi you are going to be have, which is equals to 1 by 2 pi RC. So in the case of this Wien-Bridge oscillator, we will have this what we call a frequency of oscillation as a f is equals to 1 by 2 pi RC we are going to be have here. Okay. And similarly, the oscillations will be sustained if the amplifier has a gain just exceeding 3. So that also we can calculate. So in this case, V output by V input, if we calculate, we are going to get it as a 1 by 3. So therefore, if you want to get the sustained oscillations of the amplifier, then it has to be gain which is more than 3. In this case of RC phase shift oscillator, gain should be 3. If you are having, then you are going to get the sustained oscillations you are going to get. So the general diagram of this phase shift oscillator in general diagram, if you see, so here we have this one NPN transistor, which will be there. So here, as again resistance. So these are the dividing resistors we are going to be have. This is one resistance. And here we will be connected a capacitor, which is generally the variable. And here we have this RC combination in series. Right. So this is one more resistance. So this will be output will be connected to a capacitor. This will be connected to another transistor here. So this total value is connected to plus VCC. And here, this will be connected to a emitter resistance. And here we have a combination of L and C. So this will be fed back. Right. This all these are connected to the ground. Yeah. These all are connected to the ground. Yeah. So this is a resistance R1, R2. This is the blocking capacitor. This is L, this is C. This is first transistor T1, this is second transistor T2. This is R1, C1. So this is R2, C2. So this is actually the combination, the tank circuit here. This one. Right. So this is what we have. So if you see the operation of this one, we will be applying the input signal at the transistor T1. We are going to be applied in the amplified form. It is going to be get out and plus the collector resistance RC here. So this is a collector resistance RC here we have. So, but it is simultaneously suffers a phase shift of 180 degrees in this case. A further 180 degrees of phase shift is introduced by the second transistor here. So total 360 degrees or zero phase shift will be there. So hence the feedback will be positive and circuit you are going to get self-oscillatory. So the RC element of the Wien bridge provides a negative feedback which prevents oscillations at all frequencies. So the oscillator becomes sensitive to a signal of only one particular frequency. So the Wien bridge oscillator has a good frequency stability. So this is what the Wien bridge oscillator circuit diagram which we have here. So as we have seen the frequency which we are going to get in this case is f is equals to 1 by 2, 1 by RC. 1 by RC, this is a, 1 by 2 pi RC. This is the frequency of oscillations. And the condition in order to get the what we call sustained oscillations, the gain should be exceeds 3. It should be exceeds 3. Then only you are going to get exceeds 3, then only you are going to get sustained oscillations you are going to get. So this is about a Wien bridge oscillator. So far we have studied like a RC oscillators, like a phase shift oscillator as well as the Wien bridge oscillators. Both we have studied here. Okay. So this is about oscillators. So in the next session we'll see some more topic. Okay. Here we'll stop this one.